Alright, so welcome everyone to this new video where we talk about physics and mathematics on the board. And in this video, what we are going to talk about is, again, following from some previous videos we've made on exterior algebra. So here I think we just need to focus on this previous video. And here I present a summary of what we had seen then. And so this extension I'm just going to mention is what is called the Hodge duality. And this is, as we'll see, there is a very important and interesting characteristic with it, which has to do with the cross product. We're also going to use it in many other contexts as well, but that's for a later time. All right, okay, so let's see a bit the context we are working with here. So, um, so first of all, we are in the context of exterior algebra, and exterior algebra is a sort of geometric algebra where the objects we manipulate try to have as much as possible the properties of vectors, but at the same time they are able to model or represent geometric figures. So for example, here we've got so-called k vectors, and we start by a one vector, which is here a segment which is oriented in a specific direction. So that's, I call it u. And here you can also build a parallelogram, which is made of two vectors. So the two sides of that parallelogram are u and v, and then they are repeated, to close the parallelogram. And this is represented by a two vector which is u, and then wedge product v. And this wedge product is characteristic of the exterior algebra. It's called the exterior product. And the definition of it really is that it is supposed to represent that object. And it's such that its magnitude, so the magnitude of this two vector, has to be the area of the parallelogram. Okay? So that's essentially how you should view it. And these u and v here tell you that it is built out of the vectors u and v. And likewise, you can extend that to higher dimensions. And so, for example, in 3D, you just need to do u wedge v wedge w, and you're going to have a parallelepiped, basically, object. And again, here, you just basically say that the way you characterize and represent this particular object, okay, which is a parallelotop in 3 dimensions, you say that it's made of u, v, and w, and the magnitude of this is going to be the volume of this particular parallelepiped. Now, that's basically what we had seen, and we had seen some of the properties, that there is some determinants that enter in there, because the determinant is related to essentially the volume or the area of these different objects, okay? And this can be extended to any dimension if you want to. Now, basically, what happens is that this particular object here, for example, is a subset, or can be viewed at least as a subset of an n-dimensional vector space that I call capital V. Okay. Now, these objects here, the two vectors and the three vector here, usually they are denoted lambda k of V. So what that means is that you take objects or vectors from V, and then you take the exterior product k times. Okay, so you do k times the product of some vectors of V, and you get a sort of subspace of the tensor product of V with itself, which contains all of these geometric kind of forms. Now, what the Hodge dual, which is called the star operator, actually does is that it connects the space of the k vectors. So this, let's say, the these two vectors here, it connects it to a dual space that has a lower, I mean, not necessarily a lower dimensional, by the way, a lower dimension, but that has a dimension of n minus k vectors. So for example, let's say you are in a space in 3 dimensions, then you look, let's say, at a parallelogram. So you look at a set of all possible two vectors that can be looked at, so all possible parallelograms that you can look at. And the dual of this is going to be the set of all possible oriented segments that are complementing essentially all of this parallelogram, essentially to get cuboids. Okay, so that's kind of the idea of the duality here. Now, this duality relies on the existence of an inner product in V. So you need to imagine that you have an inner product that you can denote, for example, like this. So UV in V. So you take essentially two elements of V, so that's U and V here, and you take the inner product, and this inner product is it belongs to the real, so it's a real number. Okay, so that's the first thing you need to have in order to create this Hodge duality. Now the second thing you need to do is to try to create a rule, or rather a new sort of way to obtain a number from. The problem is, how do you get a number where instead of vectors, like one vectors, you actually put this kind of objects in there, or this kind of objects? How do you do this? So essentially, I'm not going to give a name to it, because I think there is, at least I didn't see any name in various courses and notes. So I'm going to call basically a bilinear form. So it's an actual form that is going to take in basically two k vectors, okay, and then it's going to return a number. So it's a bilinear form that I'm going to call f. And again, as I said, it's going to take in two vectors and going to return a number. So the way I'm going to use it is as follows. I'm going to say f, and then I'm writing u1, u2, so that should be a wedge here, and then wedge, let's say uk, and then I v1 wedge, v2 wedge, vk. And by definition, this is going to be equal to, by definition, this is equal to the determinant, and here I'm going to say of the matrix M. And if you will, you can write M of U and V. Let's do it like this. And of course, here this is not very informative because I didn't tell you what M was. And so M of U, V. So here, obviously, I just write U and V, but you see that there is U1, U2, UK. So actually, there are multiple vectors U that are wedged together. And so here, U and V represent a collection of U, V, etc. that you've numbered with a proper index, etc. Now, MUV is actually equal to the set of elements that you're going to call Mij, and by definition, these elements corresponds to the inner product of Ui with Vj. Okay? And the only thing I forgot here is that you need to say what are the ranging values for I and j, and so this is 1 to k. Okay? So essentially, you see the matrix elements of this are going to be this inner product with V1, this inner product with V2, for example, and so on and so forth. Okay? So once we have said that, I think we are relatively set. So what we are going to look at here is first we are going to construct basically this matrix in some shape or form. So what I'm going to do is so I'm trying to find out how to do it best. We are going to look at different cases. Okay, so let me think a bit. Yeah, so the case we are going to look at here is very simple, and here is how it works. We are going to look at before we move on with calculating this, what we are going to define is a Hodge. So because maybe you don't want to calculate this stuff because you're not sure what this is used for. So we now define the Hodge dual. And so we say that for any alpha and beta, which belong to, let's say, lambda k, so they belong both to the same lambda k of V, then we have that the dual of beta is such that you have that alpha wedge star B, okay, is equal, and that's the definition, is equal to, so that determinant of M of alpha beta, and then times the, it's not a D, it's actually E, and then we've got E1, E2, and then En, where these guys here, E1, E2, etc., is orthonormal. Okay, is a cuboid, is a unit cuboid. That's the best way of characterizing. Okay. So it's a unit cuboid, and here this is that of M alpha. So that's basically a definitional feature of it. Okay, so so that's basically what we have, and that's how we actually find out what are the different forms here. Okay, so that's what we want. So what we are going to do here, I'm going to erase on that board, and then we are going to see and apply that to the case n is equal to 3 and see kind of how that goes. Okay, so now what we are going to do is basically try to find what is the Hodge dual in the case of n is equal to 3 and then k is equal to 1, and then we've got a Euclidean inner product. Okay, so first of all, the reason why I need to specify this is because this is going to enter into the matrix here, at least if we need it. Okay, so because k is equal to 1, what we have to consider is basically some alpha. So that's a 1 vector, and this alpha is equal to alpha alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. Now note that the upper indices here are actual indices. They are not kind of exponents. This is not squared or cubed. These are indices, okay? If I were to square or cube these things, I would have to put parentheses and square them and so on, okay? So likewise, we have some beta, which is equal to beta 1 E1 plus beta 2 E2 plus beta 3 E3. And again, here, E1, E2, and E3 would correspond to something like this, if you will. They are basis vectors of the initial vector space V. Okay? So that's what we have in general. Now, what I want to do is to see what would be then the matrix here, MUG. Now, what happens is that if I want to look at, for example, f of alpha beta, because that basically, this det of m alpha beta is f of alpha beta, basically. So f of alpha beta is going to be equal, and here's the only thing I can do is basically put everything together. So I'm going to have alpha 1 beta 1 and then f of E1 and then E1 and then plus alpha 1 beta 2 f of E1 E2 then plus alpha 1 beta 3 f of E1 E3 and then plus alpha 2 beta 1 f of E2, E1 plus alpha 2, beta 2, f of E2, E2 plus alpha 2, beta 3, f of E2, E3 plus alpha 3, beta 1, f of E3, E1 plus alpha 3, beta 2, f of E3, E2, and finally plus alpha 3, beta 3, f of E3, E3. Okay? And that the reason why I can write this, and that's because this is a bilinear form. So here I'm just applying the bilinearity. So B linear. By the way, I didn't show, so this is something maybe you can try as an exercise. I didn't show that this was indeed a bilinear form. Now, the determinant itself is actually a linear form, I mean a multilinear form. And then the inner product itself is a bilinear form as well. So there are reasons to think that this works, but intuitively, but I didn't show that that was the case. Here I'm just applying the property. So what we see here that we are going to get always a term of the form f of ei and then ej. Okay, and we want to see what this is equal to. Now, because this is ei ej, if I apply the definition we've got here, in principle, I need to look at, for example, mij. Okay, you need to keep in mind that mij here is going to correspond to, and in fact, I'm going to do it differently. I'm going to write ei1, ei2. I think it's preferable for later. So we've got two indices, okay? But what I see here is that you know, I don't have a choice, right? So in principle here, I can create pairs with the first vector here, and let's say the first, second, third, etc., and kth vector. And so I can create rows like this, right? However, here, in this case, I can only create a single number from it, okay? So what's going to happen is that this is essentially the determinant, but the determinant of a one-dimensional matrix. Okay, and this matrix has simply m is equal to, and that's a single number, which is the inner product of ei1, ei2. Sorry, that's a dot product, that's the inner product, so that would be like this. And this inner product is simply delta i1, i2. So essentially, if I1 is different from I2, so if the index here are different, you actually get 0. And the determinant of this delta is simply itself, delta. Okay, so that's equal to delta I, sorry, apologies. I go a bit too fast here. So that's simply equal to itself. So it's delta, and then here too. Okay, so what that means is that the Kronecker delta here, so it's 0 if I1 is different from I2, and it's 1 otherwise. Okay, so what it means to us, and I'm going to continue there, is the following. So what we are going to get here, again, is that you're going to get here 0 if they are different. So in the end, we are going to get that for any alpha beta, we are going to get f alpha beta alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3. Okay, next what we do is that we say that the Hodge dual of beta is going to have the most let's say general form possible, which is going to look like this. It's going to look like beta. I'm going to put, if you don't mind, a tilde on top just to say that the component is different. Just that if I put the star everywhere, it's going to be a bit cumbersome. So I'm going to put 1, 2, E1 wedge E2, and then plus beta tilde 2, 3, E2 wedge E3, and then plus beta tilde 3, 1, E3 wedge E1. Okay. Now you could say, oh, what's going on? Is it only these three that I can have? Yes, because in a K, if you look at the K vector space, so the lambda K of V, so the dimension of lambda K of V is going to be equal to yes, it's basically n factorial divided by so V is an n-dimensional space, and here lambda K is going to be then n minus K factorial and then K factorial. And so in our case here, it's equal to 3. If K is equal to 1, sorry, if K is equal to 2, because we're looking at this, and then n is equal to 3. Okay, so so that's what we are going to find. And so what I'm doing after that is simply taking alpha. So I've got, I take alpha wedge beta, okay, like this. And then I'm going to say that this is equal to, so I'm going to develop, so alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. So I take this like this. In principle, I could do it more generally, but it's just to show you that this is going kind of to work as well. So here I'm going then to replace by this expression. So I've got beta tilde 1, 2, E1, E2 plus beta tilde 2, 3, E2, E3 plus beta tilde 3, 1. I forgot the alpha, so no, that's fine. It was E3, E1. And what I do after that is that I take the wedge product and I distribute everywhere, okay? So what I'm going to get here is I'm going to get alpha 1, beta tilde 1, 2, and then I've got, okay. There are some terms I'm not going to put, so what I'm going to kind of remove is that, notice that if I do E1 wedge E1, this is 0. That's part of the properties that I'm going to display here. So here we've got E1 wedge E1 is equal to E2 wedge E2 is equal to E3 wedge E3 equals 0. And likewise, we've got E1 wedge E2 is equal to minus E2 wedge E1. And then E2 wedge E3 is minus E3 wedge E2. And E1 wedge E3 is equal to minus E3 wedge E1. Okay, so then what I do when I'm there is the following. I actually do this. So I'm going to say that I'm going to simply look at the terms that are going to construct E1 wedge E2 wedge E3. Okay, so I've got alpha 1 and alpha 1 E1 here. So I'm going to have beta tilde 2 3 and then E1 E2 E3. That's the first non-zero and the only one that is non-zero. Then plus alpha 2 E2. So that's then plus 3, 1, and then I've got E2, wedge E3, wedge E1. And then I've got then alpha 3. And the only one that you can work with is this one. So alpha 3, beta tilde 1, 2. And that's E3, wedge E1, wedge E2. Okay? Now, as it turns out, what I need to do after that is realize that I can swap all of these things. So for example, here, I can swap E1 and E2, and I'm getting a minus sign. So I'm going, this thing here, let's write it like this. This thing is equal to minus E1, wedge E3, wedge E2. But then this minus E1, wedge E3, wedge E2, I can swap now E3 and E2, and so that's going to be E1, wedge E2, wedge E3, so plus. And likewise here, I can do it. You need to swap again E1 and E2, and then you swap E1 and E3, and you're going to get again plus E1 wedge E2 wedge E3. So the bottom line is that you can write this as being alpha 1 beta tilde 2 3 plus alpha 2 beta tilde where am I 3 1, and then plus alpha 3 beta tilde 1 2, and all of this is times E1 E2 E3. So that's the product of this with that, and this has to be equal by definition. This has to be equal to the det of m of alpha beta times E1 wedge E2 wedge E3, okay, which is equal to, as we have calculated at the top here, it's equal to alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3, and then E1 E2 E3. Now what you have is that you have the same prefactor in front of the same kind of cuboid. You've got the same prefactor, but you don't have the same kind of symbols in front of the alphas, okay? But because the alphas are whatever we want, so it's not true for just one type of alpha, it's true for any alpha we take, then it means that we need to equate the betas here. So I know what beta 1 is, but in principle I don't know what beta tilde 2 3 is. And likewise, I don't know what beta tilde 3 1 or beta tilde 1 2 are. But because these expressions have to be equal, then I can deduce the following, that beta tilde 2 3 is actually equal to beta 1. Beta tilde 3 1 is actually equal to beta 2. And finally, beta tilde 1 2 is equal to beta 3. So we are going to see, I mean, that's kind of the main thing that is important here. And we are going to see how that works then. Okay, so now that we've got this, we can try to apply it to very simple cases. And in fact, after that, this is very easy once we have that. So the simplest one we can think of, for example, is if I have E1, okay? So if I have E1, so basically I do beta is equal to E1, then what does that tell us for what the corresponding dual vector, the Hodge dual actually is? So Hodge beta, which is equal to E1, is equal to what? So remember that Hodge beta is going to have this particular form here, okay? It's going to have this form, and then I need to check which ones are non-zero. So the only beta that is non-zero here, the only coefficient of beta is non-zero, is beta 1, okay? So then I need to look here. Beta 1 is actually equal to beta tilde 2 3, okay? Now beta 2 and beta 3 in that particular case are equal to 0, and therefore beta tilde 3 1 and beta tilde 1 2 are going to be null, okay? So the only one that is left is this, that is going to be equal to 1, and then times, so that's 2 3, and then I simply get that this is E2 wedge E3. And there you go, that's it, right? And in fact, you can do the same, so that's a kind of first case. You can do the second case, E2. So you've got wedge of beta is equal, sorry, not wedge, but dual of beta is equal to star E2. And that's going to be, if you look at it, again, the only non-zero here is beta 2. Beta 2 is beta tilde 3 1. So what we are going to get here is that this is E3 wedge E1. And finally, the one left is beta is equal to E3. And then you've got the dual of beta is the dual of E3. And then it's equal to what you're going to find here. This is E1 wedge E2. Okay, and so in fact, if you've got now any one vector that can be expressed as a sum over E1, E2, E3, etc., then you just need to apply the dual Hodge operator onto the basis vectors, and you're going to find automatically that that works. Now, one thing that I have not specified, and I'm not going to, is the following, is that the star operator, and I'm going to say for Euclidean vector spaces, V is involutive. So what that means, in case this is not clear, is that if you apply twice the star operator onto beta, you actually get beta itself. And the reason why this is important is the following, is because if I actually apply, so if I do the star of E2 wedge E3, I'm actually going to get the double star of E1, which is equal to E1. If I take the star of E3 wedge E1, I actually get the double star of E2, so I'm getting E2. And then if I take the star of E1 wedge E2, I actually get the double star of E3 and therefore get E3. Okay? Now, the reason why this is interesting is that it leads to a map, in fact, a bijection between the world of parallelograms, if you will, and basically the world of oriented segments. Okay? And in fact, what happens is that that's what the cross product actually does. The cross product is therefore definable. The cross product is definable because as an operation, as an actual product between two vectors that basically, so between any u and v, basically can be defined as being the Hodge dual operator of u wedge v. Okay, and that's how it's actually defined. Okay, and I'm just going to finish on this. The reason why this is quite fascinating is because if you ever wondered whether you can generalize the cross product in more than 3 dimensions, then the answer is no, you can't. At least if you want to understand the cross product as an operation but between two vectors that is going to give you another vector. Okay, and the reason why is because with the definition of the cross product that is defined that way, you actually use the fact that the 3-dimensional space, okay, vector space, when you take a 2 vector, so something that is made out of 2 vectors, a parallelogram, if you do 3 minus 2, you actually get 1. So the dimension of the Hodge dual is going to be 1, so that's a vector. However, if you are in 4 dimensions, for example, if you take a 2 vector that is going to be a parallelogram in this 4-dimensional space, okay, fair enough. But if you look at the Hodge dual of this parallelogram, it's going to be another parallelogram. Okay, it's going to be a 2 vector as well, because 4 minus 2 is equal to 2. Okay, so you're not going to obtain again like a single segment that is oriented. Okay, so that's why like the cross product is a really unique object that exists in the case of 3 dimensions. Okay, so I think it was busy enough, so I will leave it here. If you've got any comments, questions on some of the things that I've done here, I've been as pedestrian as possible. Usually you won't even see these different developments. People simply tell you what are the transformation rules. But the reason why I want to put them there here is because we are going to see how they change when we look at a Minkowskian space later on. Okay, so see you in the next video.